Yesterday we talked about the basics of IOPs. Today we are going to talk about the inversion of IOPs and its applications. Okay, if you ever did some exercise with remote sensing, especially go to measure the remote sensing reflectance, this is what you will get. Okay, right? You have the water-limit readings up there, and that's the downwinding irradiance. The ratio of the two give you the remote sensing reflectance. And these are the spectrum of remote sensing reflectance collected at different waters. So what's next is, okay, the purpose of remote sensing is not simply get these curves, this spectrum. We want to use these curves, this spectrum, to get the in-water properties. Like historically, the focus has been chlorophyll concentration, right? And also suspended sediments. If it's shallow water, we want to get the bottom depths, the different substrates. So basically what we really want to get is environmental information from these curves. So here today, for this lecture, the focus is how we get these. So that's that how algorithm. How to have an algorithm. Basically, we have to have a way to convert this spectrum to something we want. For this algorithm, generally we can separate them into two groups or two classes. One we call it empirical, another is called semi-analytical. Okay, empirical basically means, okay, we don't need these classes here. Empirical means just go there to collect data, collect chlorophyll or collect suspended sediment, collect a reflection spectrum. When you have enough, quote unquote, then you do regressions, you get an algorithm. Okay, basically we use that, or historically use that to do interpolations. So that's why we say for empirical algorithms, we don't need any bioptical models. We don't need what we talk about the basics of IOPs. You just do regressions. And for the empirical algorithms, also there are explicit and implicit, we call it, approaches. Explicit, just simply you have those mathematical functions presented in front of eyes. Okay. Implicit basically here means those neural networks, quote unquote, we call the black box. It's all those coefficients, all those regressions, all those relationships are embedded, hidden in those black box, in those neural networks. When you get time, you can play that by yourself. And again, the key thing for this is you have to have a large data set in order to train the neural net algorithm, neural nets, or get the regression of that empirical relationship. But that's not our focus today, okay? Because as I said, for that empirical sort of kind of relationships algorithm, you just need to collect data. You don't need to know the radio transfer. But for semi-analytical algorithm, that's the focus today. We have to know what we talked yesterday, the basics of IOPs. We have to know the radio transfer. I think that's what Kurt and Darius have showed you guys this morning. And we also need to know the relationships, okay, between AOPs and IOPs. Otherwise, we'll not be able to do it. There's a term here called semi-analytic. You may want to ask, why has to be semi or semi? Could it be just analytic? Yes, that's a dream. But I will show you why we can never, at this point, get to really analytic. It will be semi-analytic. For this semi-analytical, then we can separate them into two groups. We call it bottom-up strategy and top-down strategy. I will show you what that means, okay, for the two kind of groups of semi-analytical algorithms. As said, algorithm basically is an approach to get the outputs from these inputs. Inputs will be the spectrum of remote sensing reflectance or spectrum of water-limit radiance. The outputs will be chlorophyll, suspended sediments, shallow water depths, bottom substrates, or as today our focus will be IOPs, the inherent optical properties. If you ever read this paper, this has been cited almost, I think, 2,000 times. That's the most cited paper in ocean current remote sensing, I think. It lists a bunch of empirical algorithms, basically, for chlorophyll. Everything is about chlorophyll in this paper, okay? You have all kinds of explicit functions. Like for this one, it's basically RS at 510, 555, or RS 490 to 555. Use that as the input to get the concentration of chlorophyll. And there are many other kind of math formulas. But all these are basically a tuned relationship between remote sensing reflectance and the chlorophyll concentration. For this kind of empirical algorithm, I always want to kind of emphasize and really warn people to do regressions is some of them are just coincidental, okay, may not have a real physics behind it. The reason to say I will always use example is if you have a newborn child in a family, but at the same time we have new trees growing up outside the house. If you measure the weight of the baby and the height of the tree, you'll find a very good correlation, okay, maybe 1.0. Then can you use that really to deduce one from the other? Maybe not, okay? That's really coincidental. So when all we do this kind of empirical algorithm, it's very important really to figure out is any physics or cause and effect behind it. Otherwise, we could be really leading to a wrong path. Okay, the reason why for those kind of empirical algorithm can work for chlorophyll, it's embedded in this general relationship. Okay, these are remote sensing reflectance for different waters. Basically, you see the 440, the change of 440 remote sensing, and the change of 550 remote sensing. Basically, as you will play with the Excel file I told you, you'll see that when you increase chlorophyll concentration, 440 will decrease. At the same time, 550 will increase slightly. So then you do a ratio, kind of give you that indication. Here, when this decrease, that means the increase of concentration. The reason is simple. As we talked yesterday, the inherent optical properties. Chlorophyll has a strong absorption at 440. We have more chlorophyll, it will draw down on this at this wavelength, and also the scattering will increase remote sensing reflection at this wavelength. So that ratio gives us this nice indication of chlorophyll. If you ever read that book, recently a book by Jim Aker, talk about the history of CZCS, or our ocean current remote sensing. He will tell you that for the CZCS to be launched, it's only based on 37 measurements of regression between remote sensing reflectance or water NIR radiance and the chlorophyll concentration. Get a nice fit. Then that gives us the kind of confidence, as long as we can get a good water NIR radiance from satellite, we'll be able to do chlorophyll concentration from satellite. That's all based on kind of embedded in this. So for that purpose, and for that same kind of strategy, we can also use regressions to do IOPs, like shown here. We can use regression to do the total absorption at 440, or we can use the regressions to do phytoplankton absorption at 440. It's the same logic. You have increased absorption at 440, we will draw down the RS at 440. So that ratio, this is 440 to 550, this is 490 to 550. So a combination of these can give you that indication of the either total absorption or phytoplankton absorption. But again, these are the empiricals. It's data-based algorithm. So when you have the data, you can play all these kind of games. So that's not our focus today. Okay, as I said, for empirical algorithm, it's simply just you need money, you need time to collect data. Today we are going to talk about the physics-based algorithm or mechanistic algorithm. Okay, so as I mentioned earlier, what we measure from satellite is up the water NIR radiance, LW. ED is an incident irradiance from both the sun and the sky. So the ratio gives us this nice remote sensing reflectance. Okay, Then the first thing is, okay, how this RS is related to IOPs or biogeochemical properties. Only after we can find that relationship, we'll be able to do the inversions analytically. All this fundamentally is rooted in the radiative transfer. Okay, this is a change of radius of angle. Okay, for distance. This radius in angle, this beam attenuation, that beta is a volume scalar function. Okay, basically what this says is that's basically this in the vertical domain. Okay, what this says is this is a loss term, this gain term. I guess that I'm assuming Kurt has covered this. Here's a quick summary. So for radius, we go in this direction. Okay, for this short distance. There are some of these will be scattered out of the direction. So that's a loss term for this one. But also there are lights going in other directions. Those other directions will scatter into this direction we are focused on. So that is the gain term. So all these relationships, fundamental relationships for ocean optics, for ocean color remote sensing, it's this radiative transfer equation. There are ways to solve these. As you will learn a lot, I think, in this week, next week, it's hydrolite. Hydrolite, basically, it's really a powerful tool to solve this radiative transfer equation. Then to find the relationships between remote sensing reflectance and IOPs, find the so-called Ks with IOPs, and many other things. In addition to those I call hydrolite numerical solutions, there are also analytical solutions. The most concise and robust derivation, I think, is Ron Zanneville's 1995 derivation. It's all based on radiative transfer. Okay, it's all basically rearranged radiative transfer and using the observations of the operating field and the scattering sort of properties, and then come up with this nice generalized equation between remote sensing reflectance and these IOPs. C is the beam attenuation, beta is the phase function, and the BF is forward scattering, and these K are so-called diffuse attenuation coefficient. And all these K are also related to the IOPs. So basically here, give you a general sort of kind of a concept. Okay, remote sensing reflectance, it's a ratio of this weighted volume scalar function divided by this term. But this term is still too complex, which is not straightforwardly be useful for our analytic inversions or algorithms. So we have to, more or less have to simplify this complex equation to make it directly, easily usable. How we did. So that's also based on Kurt's hydrolite. There are a bunch of simplified equations or formulas have been generated or based on this and generated after tons of numerical simulations using hydrolite. For instance, here's the Albert Mobley 2003 paper. It's remote sensing reflection. This is a kind of coefficients. Basically, it's BB over A plus BB to the power of 4. Basically it's a power series. Okay. Then here's a Park and Rudick. Also, it's a power of 4. And here is Van der Meer and Pastor Camp. It's also power of 4. Okay. Now, you see, these are basic general sort of kind of relationships. It's some kind of basically a simplification of this complex equation to more easily usable equations or representations. One of that is our derivation is we separate that BB over A plus BB into BB water to A plus BB and BB particle to A plus BB. The reason for these two terms is rooted in the discussion we had yesterday. Remember I talked about in the open ocean, the blue wavelengths, the scattering is dominated by water molecules. In the longer wavelengths, it's dominated by particles. So there's a transition from shorter wavelengths to longer wavelengths. So basically this represents that transition from shorter wavelengths to longer wavelengths. In the shorter wavelengths, it's this term makes more contribution. In the longer wavelengths, it's this term makes more contribution. So that's a representation of that phenomena. There are also terms by lookup tables. That's Morel's lookup tables. Okay. Also, it's a remote sensing reflectance. It describes the BB over A plus BB with this G tabulates for different wavelengths, different chlorophyll, and different angles. So if you know the angle, you know the chlorophyll concentration, you know the wavelengths, then you have this G number. Okay. So that's another approach to link remote sensing reflectance with IOPs, with BB and A plus BB. Also, there are Gordon's 1988 publication or formula. It's also remote sensing reflectance. This pi means it's vertical, okay? Because as we talked about radiance angle dependent. So you have to specify an angle. Normally, we're talking about the angle is vertical, the vertical angle, okay? Remote sensing reflectance, it's basically it's a power to 2, okay, BB over A plus BB. From all of these expressions, there's one general concept. What's that? Remote sensing reflectance is a BB over A plus BB function. No matter it's a power to 4, power to 2, or 2 terms, it's a BB over A plus BB. There's no B there. So that's a fundamental sort of kind of either limitation or feature for remote sensing. Remote sensing just cannot have a relationship to the beam attenuation coefficient. It's to the back scattering coefficient. It's not to the total scattering coefficient. Simply because the photons going forward, that's the most of the strongest of scattering photons goes forward. Those photons just have no information, get to, or very limited information going back to a satellite, have that feeling. Okay, remote sensing feeling, we just cannot feel those forward scatter photons. Okay, so we have remote sensing reflectance. That's here. This we call it the subsurface. Basically, here's the surface. Satellite does not measure the subsurface remote sensing reflectance. Satellite measures sense above the water and actually passes through the atmosphere. But all these relationships here, this small r, representing subsurface remote sensing reflectance. Basically, it's just the light below the surface, the radiance below the surface, divided by the ED just below the surface. But we have, satellite has its RS. Then what's the relationship between RS and RS? Remote sensing reflectance, this above surface is water limit radius divided by ED0 plus. And the ED0 plus, it's this ED0 minus, it's a transmittance from air to water. This ED0 plus going down. There's another term for subsurface irradiance. It's internal reflection.
Yeah, you say that almost all the models are a function of this ratio BB over A plus BB. But do you mean that that's coincidental, or there is this? Is that exact? Because there was a model that has logarithm there, the last one. So I mean, why?
That's empirical.
Yeah, for example.
That's basically it's a numerical simulation empirical. Okay, right. So basically, what happens for this one? There's a fixed relationship between BB and B. So you have a fixed BB and B relationships, then that B actually represents BB.
Okay.
But that BB over A plus BB thing is really rooted here. This analytical solution. It's in that beta, what is the scalar function? It's integrated in 0 to half pi above them. So that all the integration pretty much capture 95% of the backscatter signals, not very limited, or it's a minor thing of the B forward coefficient.
Okay.
Let me repeat the question. Okay. Your question is why this equation still has B there, but I say the remote sensing reflectance is a function of BB over A plus BB, right? Okay. Kurt, you have some comments?
I was just going to say the BB over A plus BB being proportional to remote sensing reflectance comes from what's called the single scattering approximation, which is a solution to the radiative transfer equation if there's only one scattering event. And then you can show that that's the way it comes out.
I would think the best answer, I think, is this one for that. This is purely from radiative transfer equation. There's no assumption, anything. Just from this one, it shows that generally remote sensing reflectance is a function of the backscattering coefficient, not the total scattering coefficient. Okay. Colleen, you have a comment?
At the denominator, you essentially have C minus B forward, which is A plus B back.
Okay.
So
this will cancel out that B, basically. Cancel out the B forward.
Yeah.
Okay.
C minus B forward is A plus B back.
Right. So, okay, we talked about the relationship between subsurface remote sensing reflectance and the BB and over A plus BB. But satellite does not measure subsurface remote sensing reflectance. Satellite measures to the most above surface remote sensing reflectance. So we have to do a conversion between the two, above surface and below surface. For below surface, there's downwinding irradiance below surface, has a transmitting light from above the surface, also the internal reflected light by the surface. So there are two terms. This is basically internal reflection of the upwinding light, then go back into the water again. So put all these things together, we'll get remote sensing reflectance above surface. It's this transmittance term and the remote sensing reflectance of below the surface, and this internal reflection, this R is called the irradiance reflectance. Basically, it's EU 0 minus divided by ED 0 minus. We call it irradiance reflectance. After some numerical simulations with a powerful hydrolite, then generally we can get RS is roughly about 0.52 times the small RS and divided by that term. So now we see there's a one-to-one link between above surface remote sensing reflectance and the below surface remote sensing reflectance. So that also tells us remote sensing reflectance is also a function of BB over A plus BB, because this small RS is a function of BB over A plus BB. Also, for most of the waters, 99% of the world ocean, this number is tiny. It's 0.0 something. So make this number generally very small. Not small, sorry. Make this number small and make this number generally close to 1.0. So that's, if you want to say big RS approximate as 0.52 times small RS, that's not a bad assumption, okay, in general, 99% of the world oceans. So, okay, what's next? Then we have this RS. The next target or task is just to solve for IOPs from this remote sensing reflection spectrum. That's at the beginning I talked about the two strategies. One is the bottom strategy and another top-down strategy. Basically, for the bottom up, basically we are kind of building the blocks, okay, then to come up with remote sensing reflection spectrum, then compare that with the major spectrum, then try to do the solutions or retrievals. Top-down, it's kind of like you peel an onion, okay, you peel layer by layer. You peel the first layer, then you peel the next layer. I will show you what that means, okay. So generally, as I mentioned, remote sensing reflection is a function of A and BB, okay. The details you can use depends on your favor. You can use Morell's equation, you can use Gordon's equation, or you can use one of those equations I listed there. But generally speaking, remote sensing reflectance is a function of A and BB. Then remember we talked about that A has APH, ADG, BB water, BBP. So for each wavelength, we have A water, APH, ADG for detritus and gap stuff, the combination of the two. Then for satellites, we have, say, like C-waves, we have 5 bands in the visible. That means for each wavelength, we'll have an equation like this, 410, 440, all the way to, say, 670 or 555. So for each wavelength, you have A water lambda 1, APH number 1, ATG number 1, and the BBP number 1, and so on. What does this mean? Mathematically, it simply means we have a number of equations which is smaller than number of unknowns, right? For each wavelength, we have at least 1, 2, 3 unknowns for each wavelength. So you increase wavelengths doesn't mean we'll increase information. Increase wavelengths at the same time for that wavelength also have some related unknowns of the APH, ADG, and the BBP there. So if you are good at the algebra, then this tells us fundamentally this is a yield-formed math problem. Fundamentally, just actually, which theoretically we cannot solve it. And that is why I get to the beginning, why there's never analytic solutions. We have to make assumptions. We have to develop other things in order to make this soluble. That's where that semi comes from. We just cannot do it analytically, completely, purely analytically. So basically, we have to either increase the number of equations or decrease the number of unknowns. Let's say we just focus on one of them, next is the BBP. Then you can use the red wavelengths. In the red wavelengths, these two terms are negligible. We can omit it. Then you can use the red wavelengths to get one BBP. So that's a way to kind of reduce the number of unknowns. So here we're going to talk about, okay, how we can make this quote-unquote soluble, semi-analytically. One of that is the so-called, as I said, bottom-up strategy, BUS, okay? Remember I talked about yesterday, total absorption is A water plus the many components. Backscattering is the BB water plus many components. But eventually, to make it easy and lazy, we broke them down into 3 or 4 terms. One term is constant, okay? Then other 3 terms are variables. And further, because the AD and the AG are functionality is similar, both are exponentially decay. So we now put these two into one term called ADG. So now we have A as A water plus APH plus ADG. Then the approach to do that, or to reduce unknowns, is to make this APG wavelength to wavelength dependent. Instead of treating each wavelength independent, we treat them dependent. That means, okay, when I know the value at one wavelength, I can guesstimate the value at other wavelengths. Then we no longer have independent variables for APH at different wavelengths. Same thing for ADG. If I know the value at one wavelength, then assuming I can know the values at other wavelengths based on that exponential decay function. So then basically that reduces the unknowns. We no longer treat this ADG spectrum and APH spectrum wavelengths to wavelength. We no longer treat them independent. We treat them as dependent to each other. So this symbol here means basically a shape of the spectrum. Then this M1 becomes a magnitude. We use a magnitude to scale it up or scale it down of the whole spectrum. So it's all move together, up or down. We think together, we rise together. Same thing for ADG. See, that's a way to reduce unknowns. Then for this one, if we have 5 bands, we're supposed to have 5 independent variables. Now it's just one, M1. Same thing here, it's just one variable, M2, to scale these shapes. For BB, we do the same thing. We have BB water, it's a constant, then we try to find a shape, the spectral shape of the backscattering coefficient. So we use M3, this magnitude, to scale it up or scale it down of the backscattering coefficient, this spectrum. Okay, let's see details how we do this. We talked about the phytoplankton pigment absorption spectrum, as shown here as an example. You see, it's not easy to use one mass function really to represent this. There's so many features, wiggles. It's not that easy to use one function to represent the whole variations from 400 or 350 all the way to 750. So what have been doing in the past decades? Empirical. So this is where the empirical come in. That's semi-in. Empirical means this one of the popular ones. It's a breakout approach. Okay, APH represent a it describes a function of chlorophyll. This APH is here. This BPH is here. These are derived based on hundreds of thousands of measurements. These numbers, AB, are empirical values. So with this table, you give me a chlorophyll concentration. See, that's one variable, same as M1, right? You give it one variable, give a number, then you get APH spectrum based on these regression-derived coefficients. So that's a one variable approach. You just use one variable, one unknown, to get the whole spectrum of the APH curve. Another way is we use the APH 440 as an input. Same sort of kind of approach. A0 and A1 here are derived based on measurements empirically. So for this, when we know the APH 440, then I can map out basically this spectrum of APH from 400 to 700 nanometer. As here is 10 nanometer bandwidth. Here is every 4 nanometers. Basically what that says is, for this curve, as long as I know this value, I can get the spectrum of the APH curve. Is that clear? Okay. That's one parameter approach. There are also two parameter approaches. Okay. Here is an example by CLT et al. So here's APH wave, APH lambda. Then here's one variable. Here's another variable. This SF, it's a parameter, basically kind of measure what percent of picoplankton, what percent of macroplankton, basically kind of two end members. Use the two end members plus this magnitude to scale up the phytoplankton absorption spectrum. So there's a two parameter sort of kind of approach to get the absorption spectrum. There are also multiple parameter approaches. This is proposed 20 years ago by Hopfiner, Sansandranas. Basically, use a bunch of Gaussian functions. Each Gaussian function represents the absorption of individual pigments. So basically, summarize of the contribution of many pigments. Okay, so here's, for example, they used 13 Gaussian bands. Each Gaussian band has their center wavelength, half bandwidth, and their magnitudes. The magnitudes depends on the concentration of that pigments. So you sum up these Gaussian bands, you can also get a very nice absorption spectrum. Then with these many variables, say now we can get some of these details of these wiggles. Because, this mass, you have more variables, you have more freedom of control, you can add more features. The smaller the number of variables, you have less power to capture those little details. But if you play with the Excel file, you'll see when you have too many variables, then remote sensing will be a problem because those variables will fight each other. They don't know which one is right or which one is more appropriate. But anyhow, these are just approaches trying to use a few parameters instead of infinite parameters to model the absorption spectrum of phytoplankton pigments. So here's a comparison based on showing results. The hope is that using the APH 440 as a single variable. So you see for different, so this is a chlorophyll at 0.1, this is chlorophyll at 3.0, so you see the shape. The shape varies. Remember we talked about yesterday for the phytoplankton absorption spectrum. for the open ocean, it's narrow. That peak are narrow in the blue-green band. Then when we get to macroplankton, basically coastal ocean, we have lots of nutrients. The phytoplankton is bigger. Then the absorption curve is flatter or flatter. So basically, this one parameter approach can also give us some kind of those features instead of single fixed shape for all waters. We don't want to have one single spectral shape for all waters. That's not consistent with our observations. Should be a variable shape for different waters.
Yeah, I understand that, for example, in multiple Gaussian distribution, I can redo this curve of lots of peaks or strange shape, but I don't understand why can I associate one pigment for one Gaussian. If each pigment has a lot of vibration modes and absorption modes, why can I associate one absorption spectrum for one pigment?
That's remember. Okay, so your question is why can't we just have one curve, one Gaussian band for one pigment? That's the question, right? But think about there are also we talk about the package effect. Okay. The package effect will make it kind of fighter, lighter, all those things. So that can build into these general shapes. So these shapes are not fixed. It's not a constant. So those are the factors to consider. The size also can impact those things, right? So basically this shows, okay, we can use either one variables or many variables to describe the spectral dependency or spectral variation of phytoplankton absorption coefficient. Okay, that's for that one term, the APH term. Now for the ADG term, that's what we generally use today, up to today. It will use a spectral exponentially decay curve function with this S and exponential decays with wavelengths. It's all like this. But the trick is how you determine this S. For different S value, as shown here, it can be very steep or quite kind of mild with the increase of wavelengths for that reduction. How you determine this S value? We know it's roughly in this range, 0.01 to 0.02. But can we simply use 0.01 or use 0.02? Using a different numbers will have an impact as if you play with that Excel file. It's tricky. And still today, we still don't have a way really to figure out what is the right number for this water body today. Like I think the water here is quite more stable. But if you go to the Massachusetts Bay, those waters today and tomorrow could change a lot. Should we use the same number for today and tomorrow, or today and yesterday? It's a question. It's a question for all you guys. Think about it. Can we make this smarter down the road in the next 5 or 10 years? How we can really pinpoint this number should be 0.0123, not a random number, say 0.016. Another term is the backscattering coefficient of particles. Okay, also, as we discussed yesterday, we use the power law function. It's a lambda to that eta. The eta, again, it's unknown. It's not fixed. It varies from water to water. We cannot use one fixed number for all waters. But then, okay, you say you cannot use a fixed number, that means you have to use a more dynamic number, right? Then what we should use for the water here? What we should use for water in Massachusetts Bay or Gulf of Mexico or Atlantic Ocean? How that varies? How we can remotely determine that number accurately? Those are challenges. Okay, so as I mentioned at the beginning, remote sensor reflection is a function of BB over A plus BB. Now we have developed models to get APH, ADG, right, and BBP. So we put those things into this formula. This is what we get, right? Remote sensor reflectance You have M1 for APH, M2 for basically scale ADG, M3 to scale BBP. So now, remote sensing reflectance has just 3 unknowns, 3 independent unknowns, M1, 2, 3. And this has been observed, actually practiced more than 20 years ago. So basically, we have to, what we really need to figure out is how APH, ADG, and the BBP should be specified for individual, for specific locations, specific waters. So when it's only 3 variables, now if remote sensing reflectance has more than 3 bands and spread out from blue to red, then we should be able to solve for these 3 variables, right? Mathematically, then become possible. Before that, as I mentioned, we have more unknowns than equations. It's not solvable. Now with, because satellite, even from CCCS, now with models, at least we have 4 or 5 measurements in the visible domain. So that means we have theoretically enough equations to cover the 3 unknowns. Okay, so then how we derive these 3 numbers? How we solve these 3 unknowns? That's called, basically they have a bunch of range to do. It's we use a spectral optimization generally. Okay, that's a general terms used to solve these unknowns, or use lookup tables. But the spectral range usually used is a blue-green, that's Hogue and Nan color, and the binding, it will use a red infrared, as I will cover the next slide, or normally we use the entire spectrum from, say, 400 to all the way to 750, or 400 to, say, 670 for satellites. We use the entire spectrum to do optimization to solve these 3 unknowns. But now you should see what this bottom up mean, the bus. Basically, we trying to figure out each little block, the APH, the ADG, the BBP, and the RS to RS, how they are related. So we look at these individual blocks. Okay, then we figure out their relationship, we put into this big relationship, then we try to find the solutions. So like as shown here, the spectral optimization. Okay, you have the blue, it's model RS. Okay, this red, it's a measure RS, the spectrum. What we try to do is, okay, we change the values of that M1 to M3. We change the values until the model RS, this blue, match this measure RS, quote unquote, perfectly. Then we say, haha, this must be the solution for this remote sensing reflectance. The how we know it's perfectly matched. Could be subjective, you can use eyeballs. At the beginning, I just use my eyeballs, okay? When I see 2 curves really matching each other, kind of fall on each other, overlaps on each other, and I say, I have good answers. But normally, we use an objective way to measure this, basically quantitatively. This is the objective function or error function. It's a measure between the model RS and the measure RS. Basically, the root mean square error. But it's not just one wavelength. It's across the spectral band from the shorter wavelengths to longer wavelengths. When this number minimized, it cannot be small anymore. Then we call that a set of M1 to M3 as the solution for this given remote sensing reflectance. That's what this spectral optimization means. Basically trying to find the best remote sensing reflectance matching that measured or given remote sensing reflectance spectrum. Okay, that's for the general sort of kind of a strategy, okay, trying to derive the 3 unknowns, the M1, M2, M3. But also, as I mentioned earlier, in the cases, I don't care. There are many variables. I only care 1. Then we can use some special features to care just 1 variable. Like there are many studies, especially for those research looking at the blooms. okay, Bloom waters. Then they focus on this feature, this valley, okay, around 750 and this peak around 710. Basically to focus on this spectrum, this range, then to get the either chlorophyll concentration or phytoplankton absorption at this longer wavelength for really high concentration of phytoplankton situations. There are a bunch of algorithm has been developed for this, like so-called 2 bands, 3 bands, blah, blah, all those things. But the key thing is, okay, when they play with the red infrared wavelengths, if we go back to the fundamental equation, remote sensing reflectance, BB and M, the top, the denominator is BB and the denominator is absorption and BB. Then in the infrared wavelengths, because A water is so large, then this term and this term can be ignored or omitted. Then this equation reduced to RS in the red infrared domain becomes M3 divided A water plus M1 divided A pH. When it's a strong absorption, phytoplankton waters, this one could be still important. But this one, this ADG, is no longer important for those phytoplankton bloom waters. Then you do a ratio of these two at some wavelengths. At one wavelength in the red, another wavelength in red, this M3 will be cancelled out. So this ratio gives you just one unknown, one variable, just M1. Then you can just find the two pair of wavelengths, like say the 710 versus 675, or the 710 versus 750. It depends on the spectral information or sensors you choose. Then you can use this ratio to get this M1. That's the fundamental reasons for using these red bands, using that peak to get the concentration of bloom waters. It's bloom waters. It's a special case. Okay, that has been basically we call it the BOSS, the bottom-up strategy. At this point, any questions, comments so far? All clear?
So I have a question about deriving the spectral shapes of APH and ADG. So I understand you're inputting a reference wavelength and then you model the rest of the shape based on that input variable. Well, where's that variable coming from? Is that being inverted from the reflectance? Or because I don't quite understand where that number's coming from.
Which number? Sorry, I didn't
So the reference wavelength that you're putting in to then model the rest of the APH spectra, or for the ADG. So when you're talking here about
ADG or APH?
Either of them, because you have to start with this. So you're inputting a value of
at some wavelengths.
APH 440. So
right.
Where's that number coming from? Is that being inverted from the?
Doesn't matter. Really doesn't matter, because as I show here, you can use either this as a reference wavelength, or you can use this as reference wavelength, because it's all scaled by the same way.
I don't mean the choice of wavelength. It's like the absolute value. Where's that number coming from?
You mean where does that 440 come from?
Well, so absorption at 440 is something per meter. So where's that actual number coming from? Or am I not understanding?
I think that's what you want to know, basically. That's the thing you're trying to find out. So by the inversion, I think what they're asking is the value that you use to make the spectrum. Where does that come from? But that's the thing you're actually trying to find out, isn't it, basically? How much of the...
Isn't it?
Colin?
I think it doesn't matter. You choose the spectral shape, and you could normalize it to the value at 440. You could normalize it to chlorophyll as a chlorophyll-specific absorption. You could normalize it to the integrated area under the curve. It doesn't matter. It's the relative relationship at each wavelength. So you're just getting a shape. What then comes out when you estimate M, the value of that has a different meaning depending upon your initial characterization of the spectrum. If you put in a chlorophyll-specific absorption spectrum as your eigenvector, then your eigenvalue will be the chlorophyll concentration. If you put in this eigenvector that was normalized at 440 nanometers, then M will be the absorption of phytoplankton at 440 nanometers. So the actual unit that your M, your retrieved eigenvalue, comes out as depends upon the units of the spectrum that you put in, the eigenvector. And it doesn't actually matter as long as you know what it is, then you know what your retrieved value will be in terms of units. You're just looking at the shape of the curve that's important. It's
But
fitting shapes.
But I think what wasn't clear is that that's an output. That's the output.
Yeah.
Yeah, is that okay?
All right, we can talk more at the party time. Okay, good. Any more questions, comments? Okay, now we get to the top-down strategy. Okay, see, at the previous part, we talked about to build each block, we have to know the APH shape, ADG shape, BBP shape, in order to get a solution for remote sensing reflectance spectrum. But top-down strategy is a different way, it's different thinking, or different strategy, different system. See, if you look at remote sensing reflectance, it's a function BB over A plus BB. In this relationship here, it didn't specify any of the individual components. Basically, it says remote sensing reflectance, it's a bulk effect. I don't care if it's, say, this total A is 1.0 at some wavelengths. I don't care this 1.0 is 90% due to phytoplankton or 90% due to xenon. As long as this A is 1.0, then this RS will be like this, given if BB is fixed, right? Because RS measures the bulk effect. So from remote sensing, what really we can do at the first stage is we should be able to get the BB and A. Remote sensing is a measure of BB and A, not the A components. So the top-down strategy is then, okay, let's use remote sensor, get the BB and A first. After we know the A spectrum, then we say, okay, can we do with this A spectrum? Can we use that A spectrum to decompose them into A water, APH, ADG? So that's what I mean, as I said, it's kind of like you peel the onion. You peel the first layer. After peel the first layer, then peel the second layer. Those first layer will be the A and BB. The second layer will be the A components, the AX. Then why, people ask, why you want to get the total A or total BB? As I will show you later in the next section. Knowing BB and A, there are many things you can do before you know the AX. As I show, when you know the total A and the BB, you can get the diffuse attenuation coefficient. You can use that to calculate the your photozone depths. You can use that to calculate the Secchi depths. You can use that to calculate suspended sediment, all those things, before you even try to get the APH and ADG. Because some of these things, some of these environmental sort of kind of information is related to the total absorption, total backscattering, not necessarily has to know the individual components. Or certainly, we definitely want to know more, but that's a different question. We'll go from the A then to get the individual components. So basically, as I said, remote sensing is a measure of total under the water clarity, like light depths, the secondary is also measure of total. So these two really, they match in the concepts. Examples of this top-down strategy TDS include the Nocera-Stramiskis that are using KD and R to derive A and BB, the QAA to derive A and BB, Smith and al., Doran and al. Using remote sensing reflectance to invert A and BB. Because of time limitation, I will not be able to cover all of them. I will use QAA as an example to demonstrate what the TDS is. As I mentioned, in the forward model, it's A and BB make remote sensing reflectance, not the individual components. It's the individual components sum up, make this total A, this bulk optical property, then get to remote sensing reflectance. So inversion, we should be able to say, okay, From RS, you invert this arrow, okay? You invert it, then you get A and BB. As I also mentioned, remote sensor roughly is 0.05 times BB over A plus BB. So the first order IOPs we can derive from remote sensor reflectance, it's A and BB, this total bulk IOPs. So the strategy for QAA is from remote sensor reflectance, the big RS, we convert to small RS, right? From above surface to below surface. From that, we estimate this eta number. That's a particle backscattering, that's a power coefficient. Remember, we have to estimate that, we have to give a number. Either 0, either 2, or either something in between, we have to give a number. Also from this, we try to get absorption at a reference wavelength. This reference wavelength may be 550 or maybe 670. I will talk to you why. See, if we know the absorption at a reference wavelength, remember remote sensor reflectance is a BB over A plus BB function, right? Then we know A at this reference wavelength, it's straightforward to calculate BB at this wavelength. Then you just have one unknown or one equation. After you know BB at this reference wavelength, we propagate to other wavelengths by applying this eta number to here. Then we know BBP at other wavelengths. We know BBP and we know BB water and we know remote sensor reflectance, we can calculate A at other wavelengths. Straightforward. Clear, making sense? You just using remote sensor reflectance, using this relationship. Basically apply this relationship by first time you figure out the A, you calculate BB. After calculate BB, then you propagate to the other wavelengths, then you use RS at the other wavelengths and BB at other wavelengths, you calculate A at other wavelengths.
So you assume a BBP shape or a BBP model, but for the A, you assume a shape as well? Or
No, you don't assume any shape about A. The only shape you assumed is this BBP shape, as shown in this diagram. Okay, that question is, do we assume a shape for the total A? The answer is no, we don't assume any shape of total A. We actually independently derive that shape from remote sensor reflectance. The shape assumed is about this BBP spectral dependency. Then after we know the total absorption at the individual wavelengths, when they can use A at 411 and A at 443, that's two equations. Then we try to solve these two unknowns, but we have to make other assumptions. Again, it's about the shape. This basically is a ratio of ADG at 411 divided by 443. This is APH 411 divided by APH 443. Colin?
So that's where you assume the shape.
This is a shape.
Yes.
This is a shape for the individual components, but not the total absorption. Okay, what's the logic behind this reference wavelength for the absorption at this reference wavelength? Okay, here is a wavelength. Here's the total absorption coefficient. When there are no components at all, when it's pure seawater, it will be this open circle, okay? When you add something into it, add the chlorophyll, add the sedum, then the total absorption will change. The spectrum will change. But where are the most change? It's in the shorter wavelengths. Because in the longer wavelengths, pure water absorption is strong. With the increase of wavelength, it's stronger and stronger. Remember, talk about that step effect. After a few wavelengths, then a jump. After a few wavelengths, then another jump. So here you see, here's a jump, here's another jump in the 400 to 650 domain. What this shows, okay, for chlorophyll up to 5.0, that's this curve. Here is almost 200-fold of change of total absorption. But here is just a factor of 2 change of the total absorption. And that's 550 or 555. Here 640. That's only about a 20% change of total absorption. What this means, for most of the ocean waters, most ocean water, I think their chlorophyll is less than 1. That's this curve. So we can have about, say, 100-fold change of total absorption at the blue wavelengths, but we only see a tiny change at the longer wavelengths. Here is 550. There it's 640. So if we use this as a reference wavelength, that means without any other measurement, I can have a very good estimation for this absorption coefficient, given all these variations. You will see I put this range here. I say a fixed number as 0.1 at 555. How bad it can be? 25% without any tuning of these empirical whatever sense or using field measurements. So I can have quite good estimation at this wavelength for the total absorption. So if I know the total absorption here, then I can calculate the particle backscattering coefficient at this wavelength using measured remote sensing reflectance. So that's the logic. Basically, in the longer wavelengths, the total absorption, their range of variability, it's narrow, very narrow, because the domination of pure water absorption coefficient. So I can have a good estimation. Then you may think, why not use even longer wavelengths? Use 750. You can be even higher accuracy. See, that gets to the issue of satellite sensors. When you get to longer wavelengths, because of higher absorption, then the water limit radiance is getting closer to 0. Then when you have something close to 0, how good or how reliable you can get a remote sensing reflectance at that wavelength. So it's a combination of both factors. First, you have to have a very reliable remote sensing reflectance at that wavelength. Second, for that wavelength, the total absorption, its variability is in narrow range. So the selection of 550 or 640, basically it's a compromise. It's a compromise between the two factors. The total absorption is a narrow range. Also, from satellite, we have a reasonably good remote sensing reflectance for those wavelengths. So that's why in QA we use 555 or 670 as the initial wavelength or for the reference wavelength to get the absorption coefficient. At that point, basically, we start calculation here, then propagate everything to the shorter wavelengths. Clear? So, as I mentioned, knowing a lambda 0 enables calculation BBP from RS lambda 0. Then we'll propagate to a shorter wavelength. Then we get the total absorption without assuming any shape of the total absorption. Then we calculate the coefficient. In this step, we didn't model anything about the components. We don't care about the ADG shape or APH shape. We just care about the BBP shape. Then how we get the absorption at 550 or 555? That has to be empirical, because it's something we have to start. We know this total absorption is a contribution of pure water itself plus other things, this AX. So this AX we can use, we have decades of measurements, so we can use some kind of empirical relationship trying to match this, trying to get a good regressions. This is what we get so far. And this is basically a measure of confidence. How good can this be? This is known A550, and this is empirically estimated A550. Up to about, say, 0.15, we get very good regression among these two. So basically that says, okay, A550 to 0.1, that covers 99% of the oceans. So with this, we can really do a very accurate retrieval for most of the oceanic waters, basically. But this is empirical. This is not an analytical solution. So that's what that quasi-analytical comes in. It's not completely analytic. We have to have some empirical built in. So the steps of this QA is to, okay, we have a big RS that's above water, then get below water, then below water is this BB over A plus BB relationship is Gordon's formula. Then from this, basically the quadratic equation, we can solve for this U. U is BB over A plus BB. We get from RS, we can get this U. Straightforward. It's a simple math problem. We get U lambda. Then we get A550, as I mentioned earlier. Then we can calculate BB 550 from this U. Remember, U is BB over A plus BB. So you know A, you know U, you can calculate BB. But we still need this eta to propagate from 550 to shorter wavelengths. Where that eta come from? We have to give it a number. Empirical again. Here, this is from measurements, from field measurements. Basically, this is a ratio of 443 to 550. So basically, this is the empirical relationship. But as you can see, it didn't capture the variability at all. But basically just give you a trend, okay? When higher values, higher ratio means open ocean waters. Okay, higher ratio, open ocean, we get a higher number. Get to the lower ratio, coastal waters, get a lower number. It basically represents a general trend only. So if we really want to capture this variability, assuming these measurements are right, you have to do more things. Like we did, we can use neural net. We can use neural net to estimate this eta. Basically, that will use more inputs. Instead of 2 wavelengths, we can use all the wavelengths to put in a neural net to get a better estimation. But anyway, the emphasis is we have to estimate this number based on remote sensor reflectance, this way or the other way. This is empirical. So after we know BBP, then we get BB at that wavelength, put it to the U, which is BB over A plus BB. The simple math problem, you can solve for A from this U. U is BB over A plus BB, which is derived from remote sensor reflectance, right? So at this stage, then we solved A, solved BB from remote sensor reflectance without assuming any spectral shape of the components. Okay, A is these 3 components. If we pick 2 wavelengths, 410 and 440, which still have 1, 2, 3, 4 variables, still not soluble. So we have to assume shapes. Assume this shape and assume that shape. Put these 2 into this equation, now become 1, 2, is 2 equations, 2 unknowns. Now we are able to solve this. We are able to solve ADG 440, this ADG, not AG, okay, ADG 440 and APH 440. After we know the A410 and A440. But we have to assume, not assume, we have to estimate this shape number and this shape number. Fortunately, for the shape number, they're not that bad. Generally, especially for the phytoplankton absorption in the kind of blue end, the 410 to 440 range, it's in a narrow range. It's about 0.7 to 0.9 or 1.0 in that range. So it's a small range. It's not a humongous dynamic range. So again, we use a simple ratio to estimate this number, and use a simple ratio to estimate that spectral slope of ADG. Again, these are empirical. So if you want to have other better ways to improve these estimations, then the decomposition from total A will be also improved. So here are the games we should play further, how to improve these numbers. So again, I emphasize, these are empirical. These are the where that semi or quasi come in, because we just, from remote sensing alone, we just don't have enough information at this point to figure out these kind of shape numbers. Any questions so far? For the top down. Basically, it's, as I mentioned, it's first we derive the total A, total BB, then from total A, we try to derive the individual components. So 2-step or 3-step processes. Very good.
Why are you using, I mean, I don't understand why are we choosing the 443 remote sensing reflectance over the 550 for the eta coefficient of the backscattering. If this wavelength is so dependent, there's a lot of information on absorption. I mean, this 443 band is absorption is varying a lot. So, I mean, couldn't we use another wavelength?
The question is why we use the 443 550 to estimate this eta number. That's a very good question. The thing is, as I said, you can do any way. When it's empirical, you can do any way you want. The easiest, laziest, simplest way is just to use a simple band ratio to get this estimation. On the other hand, we know we are not very good on this eta estimation. However, this eta is applied to this ratio. So if, say, my target is, say, 440, 550 divided by 440, that ratio is 1.1 something. Maybe 1.2. I didn't do the calculation right there. So 1.2, if this number is 1, but I'm wrong by 50%, it should be 1.5. So 1.1 to the 1.5 power, it's not a big deal. That's a problem. That's the reason why we can tolerate some kind of uncertainties in the estimation here. Because this is applied to the ratio of wavelengths, not to the wavelengths itself. The ratio of wavelengths is much smaller number, close to 1. Think about it. If that ratio is simply 1.0, then your eta can be wrong whatever you want, right? So basically, it's a hinge. Very good question. Okay, so up to this point, we talked about the BARS and the TDS. Another little thing we want to spend a little bit of time, I think I may run over again, is we have to do a Raman correction for all the inversions, especially for the open ocean. As we mentioned yesterday, there are always Raman contributions in the open ocean, in the remote sensor reflectance. Without correcting this Raman effect, then the particle backscattering coefficient will be overestimated, and it can also propagate to the absorption coefficient. And I think that's Rosell and Darius, you guys have that built in the Raman corrections into that formula. Okay, so it's a very important component to include the Raman corrections. Now there are two ways to do this. Or actually there's 3 ways. One is just built in the retrieval systems, or you do the correction first, explicitly, then do the inversions. Here is one of the explicit way. This is total remote sensor reflectance. This is elastic component. When I mentioned RS is a function BB over A plus BB, that's only for this term, for the elastic term. It didn't consider the Raman contribution. But in the real world, measure remote sensor reflectance include this term. And this term, if you check Kerr's book and Westbury's article, it's this complex relationship. So, but then you see Raman contribution also depends on the BB and A's. So basically that says you have to know the IOPs in order to calculate this contribution. And also you have to know the ED0 plus at the excitation wavelengths and the emission wavelengths to do the calculations. This is a more kind of radio transfer-based approach, but it's more complex. The way to solve this, as shown in Westbury's paper, is to do it iteratively. You assume nothing there, you get IOPs, you get that IOP estimation, then you can estimate this contribution, subtract that off, you do the calculation again, so you can get basically iteratively to get the Raman component and get IOPs. That's one approach. Also, Darius, they have approaches built everything into the inversion formula. It's in the KD times R, or has the Raman contributions. They put that together, then it's everything included. Another explicit approach to account for the Raman, we call it Raman factor there. This is a total, this is the elastic component. Total divided by this Raman factor, you get the basic elastic remote sensor reflectance. And this Raman factor, again, can be empirically modeled based on hydroelectric simulations. The good part is this RF is roughly to the maximum about 20%. So base RF maximum is about 0.2. If this is wrong by say 20%, that means instead of get estimate RF at 0.2, you get estimate RF at 0.16. So 1.2 versus 1.16, it's a small difference. So you can tolerate some uncertainties in the empirical estimate Raman factor. Here is a kind of demonstration of the with and without Raman corrections. This is without Raman correction. This after Raman correction for the oceanic waters, open oceans. This is log of chlorophyll. This is log of BBP from MODIS. This black is a measured relationship between BB and chlorophyll. These color are derived BBP and chlorophyll from MODIS. As you can see, without a correction, Raman is overestimated. Basically, the Raman contribution is considered as part of particle backscattering. So after the correction, now you see they're much closer. This blue curve matching this black curve much closer. But we still have some uncertainties. Maybe from other things, we don't know. It's still under study. But generally, you can see without correction and after correction, the closure is much better, much improved. So back to this stage, now you should be able to understand what this ratio derived chlorophyll is. Band ratio derived chlorophyll. RS number 1, number 2, we call it chlorophyll. But you know, RS is it's a function of BB over A plus BB. So this ratio is actually ratio of the IOPs, ratio of BB and the ratio of A. So what this really is, chlorophyll, is IOP product. But in order to be more usable for biological oceanographers, we rescale them to chlorophyll concentrations, so we call them chlorophyll. But there are such large uncertainties or variations due to that between IOP and chlorophyll. There are lots of unknowns for the conversion. Like as we talked yesterday, the specific absorption coefficient of phytoplankton. And this ratio actually is a total A, which has ADG there. So that is also converted into chlorophyll. Anyway, okay, I'm running out of time again. So the key points for the inversions. First, many algorithms for IOPs have been developed. If you have interest, read that IOCCG report number 5 has lots of listed lots of practices there. And that's not the end of this game, okay? There's still bigger room for improvement. That's for you guys. That's why we have this short course, okay? And I want to emphasize the two strategies, the differences. The BAS. BAS is to build every component first, okay? Then to solve the component and the bulk properties at the same time. So for this system, because it has to assume the spectral shapes of the individual components, then it relies more on accuracy of the forward model. If the APH shape is not good, ADG shape is not good, then it will impact the retrievals. For the TDS, it's opposite. TDS derives the total first without any consideration of individual components. I mean, for the absorption component. Then for this one, it relies more on the accuracy of remote sensing reflectance. If your RS is wrong, say at the reference wavelengths, you get a BB wrong. BB wrong will propagate it all the way to a shorter wavelength, the total A will be wrong. So that these two have different emphases and different features. Okay, that's it for the talk. Now let's play a little bit game for that Excel file, okay? I hope you have already installed in your computer. Okay, in this Excel file, you see 1, 2, 3, 4 sheets, okay? The first sheet is the QAH, H for hyperspectral. It's QA for hyperspectral. The second one is the HOPE H, basically it's a HOPE for hyperspectral. HOPE is an optimization spectral algorithm, okay? This RS is a bunch of measured remote sensing reflectance, basically samples for you to play. Then the fourth sheet, the sheet is the HOPE for shallow water remote sensing or inversions. But we didn't have time to cover here. I think John and Haiti, you guys later will cover shallow water remote sensing. So basically, I leave it here for you guys to play. So if you go to Hope Edge, basically that is one kind of this bus strategy. You build the components. So you have this A0, A1, which we used to build the APH spectrum. Here's the A water absorption spectrum. Here's the BB water absorption spectrum. Then here you can see this basically shows the model. This column is B and C times log this G and the G37 is this number. Basically change this number, this whole spectrum will change. You can give a quick play. So make it a 0.5 now. Or see 0.5. You see the whole curve, the spectrum changes. Then it end up, I have curves showing here. This red is modeled remote sensor reflectance, which use these components to model. Before we change that to 0.5, actually that red matches this blue. Blue is the target very well. But now you see this red is totally in a different shape. Let's change back. Okay, change back. You go to here, basically give you the results. You have the modeled curve and the measure curve match, quote unquote, perfectly. How perfect? It's let me see. It's this number. Okay, from 400 all the way to 800, the difference is 5%. So that's basically optimized solutions. In this Excel sheet, actually all those numbers, as shown earlier, this APH for this column, this ADG for this column, then the sum up gives you the total absorption for the column I. Column J is the backscattering coefficient of particles. So you get the BB over A plus BB here. Below the surface, remote sensor reflectance. This column M for the cross surface. Then get to column N, you get the modeled remote sensor reflectance. Here O is a target. Column O is a target remote sensor reflectance. Column P, it's a root mean square measure between the target and the model. And here this chart basically shows the comparison between the model and the target. And these numbers here are you trying to derive the results. These are 1.07. It's linked to this number here. As you can see, that's R3. This number comes from R3. If you ever used Excel before, you should know what that means. Okay, if you didn't use Excel, then it may take some time to figure out what this means. To me, Excel is the best software I can use. Oh, I can code in Excel, but I cannot code in C. Okay, here this ADG, see that this is a slope, 0.0171, which is basically estimated from that empirical sense. And this 1.89 is from R8. It's also an estimation from simple that band ratio. As shown here, this S, this Y, basically it's an estimation. Okay, this is basically, it didn't estimate, I just gave a number. Now what you can see is, okay, you can play with this by change this ADG at 440, change this number. What we have number is 0.013. Let's change it to 0.02. Just watch this red curve, right? Or you change the BBP at 440. Part of backscattering. What we have is 0.002 here. If we change it to 0.005, what do you see? You see the curves, basically the whole spectrum will be modified, will changed further away from this target remote sensor reflectance. So it's basically, you can see it's not optimized. When I was doing this inversion at the beginning, I do all of this with my eyeballs. Okay, I just sit there, last thing to do, just change the numbers to see until I see my eye tells us match very well. But actually now in Excel, it can do it for you. There's a very powerful feature called solver. I don't know if you have that. Depends on your Excel version. It's in data. Under data, there's called solver. Before you guys come here, I send the email to Renisha and it's supposed to get to all you guys before I want to install this feature in your computer, laptop. You go to solver, okay, you pick this. It's already designed for you. What I have this is an objective location, that R9. R9 is this error number. That's this R9. We try to minimize this location. It's this number. This is the objective function. We want to minimize this by changing these numbers. These are our target, what we want to retrieve. Okay, so as you can see in that, these are the numbers we want to change. This is the number we want to minimize. After these are set up, you simply click this solve. Then it will do it for you. See the result? It was like this, right? After that, computer did this optimization for us, then we get a very good match. For all the numerical solutions, you have to give us number first. Okay, we call it initial values. Here, I have the column P. These are the initial values. Basically, it's a random guess based on some empirical knowledge. You just simply copy. You have to paste the values. Okay, paste the values. That gets you the initial solution. It's not good at all, right? It's far away. But then you go to solver. It's already set up. Don't need to change anything. Just click solve. You get results. So now, for the next 5 minutes, you go to RS page, copy any one of those spectrum into here. Basically, change the target remote sensing reflectance. Do what I did again to see what you got. 5 minutes. Okay.